Welcome back to Talk Tensors, everyone. Today we're looking at a paper about robots and humans, how they can learn from each other, especially in rehab. Think robot physical therapists.
Oh yeah, for sure, robot PTs. This paper is called Human-Machine Co-Adaptation Model and its Convergence Analysis. And it gets at a really cool problem, how to actually design these robots so they adapt to each patient.
Right, exactly. So it's not just like pre-programming the robot with a set of exercises. We're talking about making the robot like an active participant in the rehab, almost like a dance partner, where both the robot and the person are learning and adjusting their moves, as they go.
Yeah, like a dance partner. That's a great analogy. And this paper, it's really unique because it's not just like proposing this idea. They actually develop a mathematical framework to figure out how this co-adaptation can really work. It's called the KMDP model, which stands for Cooperative Adaptive Markov Decision Process.
Now, I know a lot of our listeners are familiar with MDPs, Markov decision processes. But just to do a quick recap, it's basically a way to model how we make decisions, especially where your actions, they have consequences that play out over time, kind of like those choose your own adventure books, but with math.
Yeah, exactly. And what the CMDP model does is it basically takes that MDP idea and then it applies it to situations where you've got two decision makers, in this case, the robot and the patient, and they're both adapting to how they interact with each other.
So it's not just about the robot making the best choice for the patient. It's more about finding a way for both of them to learn and improve as they go. It's like a two-way street.
Right. The information's flowing back and forth. And one of the really big things these researchers did is they proved mathematically that under certain conditions, this VMDP system, it actually converges to a stable state. So basically, the robot and the human, they eventually find a way to interact that's good for both of them.
So it's not just like a cool concept. It's got hard math behind it, which is impressive. Now, we've talked about the history of robot-assisted rehab before, but just to give us some background, how did we even get here? What were some of the early wins and challenges?
Right. So this idea, it's been around for decades. Early systems, they actually did have some success, like in stroke rehabilitation. But a lot of times, they just couldn't adapt to each patient. It was like, here's the robot, just do what it says, which, wasn't always that helpful.
Yeah, I can imagine that would be really frustrating, especially if you're already dealing with a lot, to not have that personalization.
Exactly. And that's where machine learning, especially reinforcement learning like RL, it's really changed things. Now we've got robots that can actually learn from how they interact with patients, and they can change how they behave based on that.
I'm curious about that idea of convergence you mentioned. How do the researchers actually measure? How do they even make sure that the robot and the human are going to get to that stable point?
That's a great question. And that really gets into the nitty-gritty of the math in the paper. They use some tools from game theory and control theory, and that helps them define these specific conditions, and they guarantee the system will hit that stable state.
So they're not just saying, hey, this will work. They've got the analysis to back it up.
Exactly. And one of the key things they use is what's called Nash equilibrium. Think of it as the point where neither the robot nor the patient can do better, can improve their strategy without making the other one worse off.
So it's kind of like finding this balance where both the robot and the human are like, okay, this is good.
Exactly. And what's interesting is they looked at two different ways this could work. One is simultaneous, where both the robot and human adapt at the same time, and the other is alternating, where one adapts and then the other. And they found that the alternating one is better. It's less likely to go back and forth wildly, so it's better suited for rehab.
It's like finding that rhythm in the dance.
Yeah, that's it.
It sounds like getting the right mix of adapting and being stable is super key.
Oh, absolutely. Too much adapting, and you could end up with the system that's just always changing, and that would be confusing for the patient. But then too much stability, well, you might not see them make the progress you want.
So it's that sweet spot where the robot adapts enough to what the patient needs, but also keeps things consistent enough for them to feel good and make progress. That's fascinating.
And that's what makes this paper so cool. It's not just, build a better robot. It's like, let's figure out how humans and robots work together and how to make that relationship work really well for both sides.
I want to dive more into the specifics of how they actually do that, the strategies for this co-adaptation. But first, let's take a quick break, and then we'll come back and get into those details. And then, of course, we'll wrap up with novel notions.
So one thing that really caught my eye in this paper was this idea of a less greedy approach for the robot, which, at first it's kind of counterintuitive, right? wouldn't you want the robot to always be picking the action that's best right now for the patient?
Yeah, my first thought too was, shouldn't it always go for that, like, I don't know, the quick win?
Yeah.
But I guess there's got to be more to it.
Oh, definitely. See, in traditional reinforcement learning, RL, the goal is usually just to get the most reward as fast as possible. But in a co-adaptation situation, that might not be the smartest way to go.
So why would that be? Why would a less greedy approach actually work better here?
Okay, think about it from the patient's point of view. If the robot's always switching things up, always looking for like the absolute best move at every second, that could really mess with how the person's learning.
Right. It'd be like having a PT who keeps changing the exercise or the instructions. You'd never get comfortable.
Exactly. And that's one of the cool things this paper points out. Sometimes doing something that's not the best right now can actually lead to much better results overall in the long run.
So the robot, by not being so greedy, it's giving itself the chance to try out more stuff, which might help the patient improve more.
Exactly. And another benefit is it helps reduce how often the patient's own policy has to switch.
Now, when you say policy, you mean like the way the patient is adapting their behavior in response to the robot, right?
Right, exactly. And if the robot keeps changing its approach, the patient's going to have to adapt more often too, which can be tiring, and it makes it harder to learn.
It's like trying to learn a dance, but your partner keeps changing the steps.
Perfect analogy. And especially in rehab, you want things to be consistent. You want people to feel like they're making progress. So having the robot not make such sudden changes is really important.
So by not being greedy, the robot's making the learning environment more like stable, predictable for the person, which could mean faster progress, right?
That's it. And they actually showed this in simulations. The less greedy approach led to better performance, A&D, less switching, that's pretty significant.
It really shows that you got to think about the long game, not just the immediate payoff, especially in this co-adaptation setting. Now, something else that I thought was interesting was the idea of model simplification. What's that about?
So one of the tricky things in machine learning is models can get really, really complex, especially when you're dealing with stuff like humans and robots interacting. And if a model is too complex, it becomes hard to understand, to interpret, and then to actually use it in the real world.
It's like trying to read a book in a language you don't know. You see the words, but they mean nothing.
Exactly. And in this case, the language is all the math and algorithms that make up the model. So simplifying the model means trying to make it more manageable without losing its accuracy.
So like translating that book into something you can understand, basically. How do the researchers go about doing that?
They talk about two main strategies, and both of them are about reducing how complicated the model is while still making sure it works. The first one is called policy pruning, which is basically like getting rid of policies that probably won't lead to good outcomes.
Like cleaning out your closet, getting rid of clothes you never wear.
Exactly. And here, the clothes are all the different policies the robot can choose from. And to decide whether to get rid of a policy, they look at its estimated value, which comes from how well it's done in the past and the overall goals of the rehab program.
So if a policy keeps leading to bad results, it gets tossed out. So the robot has fewer options, but better ones, right?
Right. And this pruning, it can happen while the robot's working, like it's constantly evaluating and adjusting, or it can happen before you even use the robot, like a more thorough cleanup.
So it's like the robot's always learning and making better decisions. And the second strategy, state reduction. What's that?
So that one's about cutting down on the number of states the robot has to think about when making a decision.
When you say state, you mean all those factors the robot has to take into account: the patient's position, how they're moving, their muscles, all that stuff, right?
Exactly. In a complex model, there can be tons and tons of possible states, which makes the model really hard to work with.
Like trying to use a map that shows every single building and alleyway to navigate a city. Way too much information.
Yeah. So state reduction is like simplifying that map, focusing on the important landmarks, the stuff that really matters, without losing sight of where you're trying to go.
So instead of tracking like every tiny movement the patient makes, the robot could focus on a few key variables that are really important for that specific rehab exercise.
Exactly. And the researchers showed that this simplification, it really works. They were able to make the model way less complex without it performing much worse.
That's awesome. You can have a robot that's both smart and efficient, which is really important if you want to actually use it in the real world. So what about those novel notions inspired by this paper? What crazy ideas has this research given you?
Okay, folks, remember, this is just us speculating, having some fun, thinking outside the box.
Disclaimer noted. Hit me with your wildest notion.
All right, so What if we could take this co-adaptation idea beyond rehab? Like, what if we applied it to other places where humans and robots work together?
Like what? Give me an example.
Okay, imagine a factory, right? You got robots working alongside human workers. Instead of just programming those robots to do one specific task, what if they could learn from the humans and adapt their behavior to make the whole thing work more smoothly?
So like a robot apprentice learning from the master craftsman.
Exactly. The robot could watch how the human moves, figure out what they need, and then adjust what it's doing to help out. It'd be a real partnership, both the robot and the human learning and getting better together.
That's a really cool idea. It's like blurring the lines between human and machine, making it a more integrated team.
Yeah. And it could lead to big improvements, like getting more work done, being safer, even making people happier at their jobs. Because let's face it, nobody wants to work with a robot that's just rigid and uncooperative.
For sure. It'd be like having a coworker who never listens or tries to adapt to how you work. Okay, for your second novel notion, let's get even weirder.
Okay, this one's out there, but just hear me out. What if we could use this co-adaptation thing to make robots that help us understand ourselves better?
Whoa, that's deep. I'm intrigued, but also kind of scared. Like robots reading our minds.
Not necessarily mind reading, but what if, by interacting with us, robots could pick up on patterns in our behavior, our strengths, weaknesses, even things we don't realize we do?
So like a robot therapist who gives you totally unbiased feedback, no judgment or anything.
Exactly. The robot could look at how we move, how we talk, our facial expressions, even our heart rate and breathing, and use that data to give us personalized feedback.
That's a fascinating idea, but also kind of creepy. But I can see how it could be really useful for self-improvement.
And since robots don't have all the biases and emotional baggage we humans do, they could give us a truly objective view of ourselves.
It's like a mirror, but it shows you not just what you look like, but also who you are on the inside.
Exactly. And that kind of self-awareness could be huge, helping us understand ourselves, have better relationships, make smarter choices.
I love these ideas.
Yeah.
They really show how co-adaptive robots could not only help us with physical stuff, but also help us grow as people.
And that's why this research is so exciting. It's not just about building cool robots, it's about exploring how humans and robots can work together to make our lives better in all sorts of ways.
Well said. Now, before we wrap up, just a reminder that we'll be back next week with another deep dive into a cutting-edge paper.
And as always, we encourage everyone to check out the full paper we talked about today. You'll find the link in the description.
Until next time, keep those brains buzzing. You know, it's amazing to think, like just a few decades ago, robots that could learn and adapt with humans, that was sci-fi, right?
Totally. I mean, it was pure science fiction, and now here we are, not only building them, but like really figuring out the theory behind how they work.
And this paper we've been talking about, it shows that shift from robots as just, programmed machines to robots as partners. It's a whole new era of how humans and robots can interact.
Yeah, for sure. And a huge part of that is co-adaptation, right? Designing systems where both sides, the human and the robot, are always learning and adjusting how they behave based on each other.
Like a dance where both partners are kind of leading and following at the same time, constantly responding to what the other one's doing.
That's a perfect analogy. And that's what makes co-adaptation so tricky, so interesting. We got to think differently about how we design robots, how we even interact with them. We can't just give them a set of rules and expect them to be perfect in every situation.
The world's messy, it's unpredictable. We got to give robots the ability to learn and adapt to that, all the little things that come up.
And that's where this paper is so important. They didn't just come up with a model for co-adaptation, they proved mathematically that this model actually works. It can reach a point where both the human and robot are learning and improving together.
So it's not just like a good idea, there's actual solid science behind it.
Exactly. And that's what makes me so optimistic about all this. We're not just messing around, we're really building a deep understanding of the fundamental principles of how humans and robots interact.
Now, you mentioned communication earlier, how it's important for co-adaptation. Obviously, these robots aren't chatting with patients, but there's still a ton of information being passed back and forth, right?
Oh, absolutely. It's just a different kind of communication, more subtle. It's all about sensors and feedback mechanisms, even little cues that humans and robots pick up on when they're physically interacting.
So, like, the robot might sense if the patient is having trouble with an exercise and then, like, adjust how much it helps or slow things down.
Mm-hmm. Exactly. Or it might pick up on a slight tremor in the patient's hand and use that to fine-tune its movements, to keep things smooth and steady.
It's wild to think about how technology can enable that kind of silent communication. It's almost like building a bridge between what the human wants to do and what the machine can do.
And as technology keeps getting better, I think we'll see even more advanced ways of communicating. Imagine robots that can not only sense how we move, but understand our expressions, our tone of voice, even our brain activity.
Okay, now that's getting into like serious sci-fi territory. But I gotta admit, it's exciting to think about.
Imagine a robot therapist that knows when you're frustrated or tired, and it changes its approach to help you, maybe offer some encouraging words or suggest taking a break, or a robot assistant that can figure out what you need based on your mood and proactively offer to help.
Like having a partner who doesn't just get what you're doing, but what you're feeling, what you're thinking.
Exactly. That kind of empathy could completely change how we use technology. It'd be a much more natural, more helpful relationship.
So as we wrap up this deep dive, I think it's important to remember that with any new tech, there are always challenges and ethical stuff to consider. What are some of the things we should be thinking about as we develop and start using these co-adaptive robots?
That's a really good point. It's super important to have these conversations early on. I think the biggest thing is safety. We need to make absolutely sure these robots can interact with people without causing any harm, physically or emotionally.
Absolutely. And we also need to think about the impact on jobs. If robots can do things that humans used to do, what happens to those jobs?
That's a real concern, and we need to figure out how to handle it. I think the key is to think of these robots not as replacements, but as partners, tools that help us do our jobs better and safer.
I agree. The goal should be to build a future where humans and robots work together, each bringing their strengths to the table.
That's right, and I think this paper gives us a really useful way to think about designing and using those kinds of collaborative systems.
This has been an incredible deep dive into the world of co-adaptive robots. This technology could be huge, not just in rehab, but in so many other areas.
Couldn't agree more, and I can't wait to see what's next. It's a really fascinating field with so much potential to make a positive impact.
To all our listeners, check out the full paper, the links in the show notes. And as always, we'd love to hear your thoughts, your own novel notions about all this.
Thanks for joining us on this journey into the future of robots and humans working together.
Until next time, keep exploring, keep learning.